Hi, everyone. My name is Vigna Ramesh, and today I'll be presenting my work with Dr. Anton Kolinin on unsupervised context-driven question answering based on link grammar. So before we get into our proposed question answering, or QA, architecture, I'd like to step back and look at the big picture that motivates our work. First is general conversational intelligence. GCI can be considered one of the core aspects of AGI, but there currently exists minimal overlap between the disciplines of AGI and natural language processing, or NLP. Only a few AGI architectures can comprehend and generate natural language, and most NLP systems rely on either hard-coded specialized rules and frameworks that can't generalize to the various complex domains of human language, or on heavily trained deep neural network models that cannot be interpreted, controlled, or made sense of. Moreover, the majority of AGI frameworks that do possess some level of natural language comprehension or understanding often cannot convey such knowledge in natural language without template-based customization or similar manual, labor-intensive procedures. The next motivation is interpretable language processing, or ILP, which is also referred to as INLP. To understand what ILP is, we have to start with XAI, or explainable AI, which requires the output of an AI model to be comprehensible to humans. Interpretable AI, or IAI, expands upon XAI by calling for an interpretable model or knowledge base, as well as explainable results. In other words, IAI gets rid of the black box model in AI. The extension of IAI to NLP is what we call ILP. As I'll explain later on, our architecture is one of the first ILP methods for QA, and as such may bring a greater degree of GCI to proto-AGI NLP pipelines. Now for some more background. Natural language generation, or NLG, is the task of producing linguistic content, most often in the form of grammatically and morphologically valid text, from semantic and/or non-linguistic data. Even the process of producing simple sentences, a subproblem of NLG known as sentence generation, which we'll treat as synonymous with NLG for the purposes of this presentation, requires significant grammatical, syntactical, morphological, and phonological knowledge. It's important to note that our NLG component of our current QA pipeline focuses on the use of solely grammatical knowledge. Within the sentence generation process is the task of surface realization, which is concerned with the construction of sentences from the underlying content of a text, usually structured as an unordered set of tokens, which are words, punctuation, etc. Question answering refers to the ability for machines to automatically answer questions posed in the form of human language. Let's take a look at this diagram here. An explainable QA pipeline involves components for both NLC and NLG. During NLC, the question or input query is parsed and then semantically interpreted, which means the pipeline determines the underlying themes or topics of the question and then computes relationships between each component of the parsed query. During NLG, the query is then semantically executed. So the semantic relationships obtained during NLC are used to find the answer to the question. And finally, a formal grammar is utilized to construct a grammatically valid sentence from words associated with the non-linguistic answer obtained in the query execution step. Our current work is concerned with a more basic version of QA, in which the query is proposed as a list of seed words in natural language, and the answer is a grammatically valid sentence that correctly captures the relationships between the seed words. In this sense, our work replaces the semantic interpretation and query execution components of this described QA pipeline with an extended version of sentence generation based on the context of the question and the scope of textual data to search for an answer. That is, we treat the context of the question as a constraint for the generation phase of QA. In the perspective of this pipeline, shown here, it is as if the words needed to answer the query are already known based on prior semantic query execution and must simply be arranged into a grammatically valid response. Given that most modern search queries online, such as Google, Bing, and Yahoo queries, are performed only with keywords rather than properly structured sentences, we anticipate that our work would be practical for human-computer interactions. Link grammar, or LG, is founded upon the fact that each word is defined by a set of connectors and disjuncts associating those connectors. Connectors serve as either the left or right half of a grammatical link of a given type, and disjuncts are sets of connectors that define the valid grammatical context of a given word. Rules, which represent lexical entries or grammatical categories, describe the sets of defining disjuncts for clusters of grammatically equivalent words. From our perspective, NLG is the process of following rules to construct sentences by matching connectors between words to form links. LG also imposes two additional constraints: the planarity meta rule, which specifies that links must not cross, and the connectivity meta rule, which dictates that all links and tokens in a sentence must form a connected graph. Furthermore, unlike most alternative grammar rule dictionaries and APIs, such as spaCy and universal dependencies, or UD, LG does not require grammar rules to be hard-coded into client-side architectures. And LG rules can also be learned dynamically through an unsupervised language learning pipeline. Overall, the human-readable and editable nature of LG allows our grammar induction algorithm to comprehend and process text under the premise of unsupervised language learning, and thereby better serve as an INLP method for the purposes of the QA task. The proposed NLG and QA methods can be called unsupervised, since they do not require prior training on supervisedly prepared corpora. However, the majority of published natural language generation methods are supervised and will rely on deep learning models that require extensive training on labeled data. As such, they are black box algorithms that are neither explainable nor interpretable, and 3 examples are listed here. There are only a few notable unsupervised, yet often not interpretable, NLG systems. Leon et al. Proposed SegSim, an approach based on the OpenCog NLGen software that constructs sentences by satisfying constraints posed by inverse relations of hypergraph homomorphisms. SegSim performs surface realization by matching the subsets of an atom set in need of linguistic expression against a data store of sentence, link parse, RELX relationship set, and atom set tuples, produced by OpenCog's NLC software. SegSim constructs simple sentences unproblematically, but becomes unreliable for more syntactically complex sentences, for example, those involving conjunctions. Freytag and Roy propose an unsupervised NLG system in which denoising autoencoders are used to construct sentences from structured data interpreted as corrupt representations of the desired output. The denoising autoencoders can also generalize to unstructured training samples to which noise has already been introduced. There exists a variety of well-known, large, supervised language understanding models that have been applied to the QA task: BERT, Distilbert, Luke, Electra, and Roberta and Bart, to name a few. However, all such models are supervised and uninterpretable. There are only 2 notable published methods for unsupervised QA. Lewis et al. Propose an unsupervised QA method whereby context, question, answer triples are generated unsupervisedly and then used to synthesize extractive QA training data in closed format. Perez et al. Developed an unsupervised QA approach focused on decomposing a single hard multi-hop question into several simpler single-hop sub-questions that are each answered with an off-the-shelf QA model and then recomposed into a final answer. Now on to the methodology behind our proposed architecture. To perform QA in an unsupervised and interpretable manner, we adopt and extend the generator architecture proposed in our previous work. After calling the loader, which is a utility infrastructure to store the LG dictionary in memory, the generator performs surface realization with these 3 steps. First, given a list of words, the generator computes a subset of all orderings of those words that satisfies initial checks of the planarity and connectivity meta rules. Then, the generator checks if each ordering is grammatically valid by ensuring that every pair of consecutive tokens can be linked via a pair of connectable disjuncts. And finally, the generator formats those orderings that are valid into sentences. We propose a contextual generator, or CG, architecture, which extends our prior generator model in 2 major ways. First, the generator model for surface realization, described on the previous slide, is expanded recursively to build grammatically and morphologically valid sentences from 2 or more seed words that comprise only a subset of the total list of words needed to construct the final sentence. Second, to allow for semantic disambiguation, or determining which of multiple sentential answers to a given query is most appropriate in the given context, the revised loader architecture, besides loading the LG dictionary and corpus lexicon, also loads context lexicons. Each word in the context lexicon is supplied with a weight denoting its contribution to the context in accordance with Zipf's law. Note that the loader creates the corpus lexicon only once, but builds a new lexicon for each unique context. This diagram shows that entire CG architecture and the different algorithms that come into play. So 2 sample question answer pairs with answers generated by our CG architecture are shown here. As you can see, the CG generates correct answers, but as demonstrated by the first question answer pair, succumbs to the grammatical ambiguity problem that I'll discuss near the end of this presentation. The CG performs closed domain QA on queries structured as lists of seed words. It operates as follows. Step 1. The CG calls the loader to store the LG dictionary and corpus lexicon, as well as extract a context lexicon from a given document, as described previously. Step 2. The CG then recursively calls the generator to determine valid sentence constructions from a list containing all seed words and n additional words from a subset of words in the context lexicon that satisfy initial checks of the planarity and connectivity meta rules. The n addition permutations are tested in order of decreasing Zipfian frequency, corresponding to the current context. If a valid sentence is found, the CG returns that sentence and stops running. When step 2 is first executed, n equals 1, imposing the constraint that the answer is of minimum length. Step 3, if no sentences have been generated after testing all valid subsets, and the runtime has not exceeded a limit specified to avoid combinatorial explosions, which we've set to 3 minutes after experimental testing, the CG increases n by 1 and repeats step 2. So on the previous slide, we saw that the CG checks n addition permutations in order of decreasing Zipfian frequency. To motivate this, consider the sample query mom cake, along with the context specifying the food preferences of family members. If the CG were to use context word frequencies without modification, rather than Zipfian frequencies, it would perceive the sentence cake was a mom as more contextually appropriate than mom likes cake, which of course is the ground truth answer. This is due to a phenomenon known as Zipf's law, which states that the rank frequency distribution of words in a given lexicon is an inverse relation. So determiners and linking verbs, such as the, was, and is, are more common in any corpus, regardless of context, than more semantically appropriate words, such as likes in this context of food preferences, as in the motivating example I just employed. To account for Zipf's law, we use the Zipfian frequency, which is calculated according to this equation. For word W of I, fx of W of I is the word's context frequency. Fc of W of I is the corpus frequency. Because the Zipfian frequency divides the logarithm of the context frequency by that of the corpus frequency, more contextually appropriate words receive higher scores than do determiners and similarly common words. For multiple word additions, we sum individual Zipfian frequencies. Now let's move on to evaluating this architecture. To evaluate the proposed architecture, we report 4 scores. First, the bigram variant of blue, a measure of the number of matching bigrams in 2 sentences. Second, WVCS, or word-to-vec cosine similarity, calculated as the cosine of the angle between the vector encodings of the candidate and reference sentences. Third is WER, or word error rate, which is a measure of the edit distance between 2 sentences. WER is calculated as the number of substitutions plus the number of deletions, plus the number of insertions needed to change the candidate sentence into the reference sentence, all over the number of words in the reference sentence. Fourth, TER, or translation edit rate, is another measure of edit distance that is calculated as the number of total edits over the number of words in the reference sentence. Note that higher blue and WVCS scores indicate higher accuracy, but lower WER and TER scores indicate more accurate language models. Each metric is calculated for each pair of candidate and reference sentences and then averaged over all 60 queries. So our algorithm was primarily tested on the 60 queries with words all part of SingularityNET's small world POC English corpus. For this purpose, we have used a corresponding small world LG dictionary, which was automatically inferred from high quality LG parses created by SingularityNET's ULL pipeline. Our QA architecture significantly outperforms prior state-of-the-art models on the POC English dataset for the task of QA from short lists of seed words. As baselines, we implemented BERT, Electra, Distilbert, and Roberta models that were pre-trained on the Stanford question answering dataset, or SQUAD 2.0, and then fine-tuned on the POC English corpus. Our QA system attains superior blue, WVCS, and TER scores and competitive WER scores, demonstrating a 0.11 increase in blue, 0.15 increase in WVCS, and 0.08 decrease in TER from the best baseline results. Our results were mainly affected by the issue of grammatical ambiguity, a problem whereby the same word can take on different roles in a sentence. For example, saw can take on both noun and verb forms, as shown here. In scenarios where multiple sentences are returned by the CG, all sentences will be grammatically valid, but only one is semantically correct. Implementing semantic disambiguation as part of the NLG component of our pipeline, beyond our use of Zipfian frequencies, will be part of our future work. In summary, we propose a novel CG architecture to perform basic QA from lists of seed words. Our algorithm is an INLP method and largely outperforms current state-of-the-art QA models on the POC English corpus. Because the proposed architecture uses LG to enable machines' understanding of text, it contributes to the reconciliation of NLP and AGI. Our QA architecture will primarily be applied to the AI-Agent's social media intelligence platform. If integrated into the AI-Agent's cognitive architecture, which currently depends on artificially controlled language similar to oversimplified pidgin English, our algorithm could provide GCI to AI-Agent's chatbots. Our future work will involve 1, testing our algorithm on queries from arbitrary English documents using the complete LG dictionary. 2, implementing semantic disambiguation. 3, expanding our algorithm's QA capability by building an integrated LG schema containing semantic as well as grammatical knowledge. 4, implementing the full QA pipeline, including semantic interpretation and query execution, preceding response generation. And 5, adding support for languages other than English, including languages such as Russian that require heavy morphology usage. Here are QR codes that link to our code base, which is all under the MIT license on GitHub, and a PDF copy of our paper. Thank you for listening.